Welcome to SDN Tech Networking Podcast, world's first human-curated AI podcast.
If you've been wrestling with enterprise networks lately, you probably know that word, simplicity. Well, it often feels like a distant dream, right? We need all these advanced features, traffic engineering, superfast failover, network slicing, but getting them usually means piling on complex protocols. So today, we're going deep on a technology that aims to flip that script. Segment routing over IPv6 or SRv6, our mission. To cut through the hype and understand this paradox, how can SRv6 deliver features we've struggled with, yet claim simplicity?
Yeah, it's a fascinating journey SRv6 took. Segment routing first showed up in service provider backbones. It was introduced mainly as an MPLS replacement, the big goal being state reduction in the core, minimizing that complexity. But then that same architectural elegance, that stateless simplicity that worked for huge carriers, that's exactly why it started making inroads, forging into enterprise networks.
Okay, so that's the big question we're tackling for you, the listener. If SR started in massive telco networks, how does it actually help your typical enterprise complexity without just adding new headaches? Let's merely unpack this. Starting with the basics, what exactly is segment routing? According to the folks at CNTech Forum, it's a network architecture leveraging the source routing paradigm. That source routing part sounds key. The goal seems to be a unified end-to-end policy-aware network infrastructure, but crucially, over a stateless IP fabric. Simplicity and scale.
Exactly. And the absolute core concept making this possible is the segment. Instead of, every router in the middle keeping track of state for every path, the source node itself dictates the path. It steers the packet using a controlled set of instructions. We call these segments.
Instructions.
Okay, think of a segment like a single self-contained instruction. It's defined by a SID, a segment identifier. And this instruction is only executed locally, right at the specific node that owns that segment. That's the clever bit. Intelligence moves to the edge.
Right. So the core stays dumb, or rather stateless.
Pretty much. And what's really powerful is what that segment, that instruction, can represent. It's not just go here. It could be a simple topological stamp like, next hop is writer X, sure. But it can also be a service instruction. Or, and this gets really interesting, a completely user-defined function.
User-defined. Wow. We'll definitely need to circle back to that.
Absolutely. And this flexibility lets us simplify. SR has two main flavors. There's SR MPLS, using MPLS labels for segments. And then there's SRv6, which puts the segment information right into the IPv6 address itself.
And the momentum seems to be with SRv6.
Definitely. Because with SRv6, you get one single, clean, end-to-end data plane. It's all just IPv6. No translation layers, no complex stitch points.
So you simplify the data plane. Where does the complexity go? If we're removing protocols, how do we still get those advanced features?
That's the less is more beauty of it. It's about what you get to remove. Think about the stack simplification. With SRv6, you essentially eliminate the need for MPLS at the host level. You ditch RSVP-TE for your traffic engineering and fast reroute. You don't need things like NSH for network function virtualization service chaining. And maybe most importantly for day-to-day operations, you remove LDP.
Removing LDP, okay, that gets attention. That protocol can be a real beast for troubleshooting state issues.
Exactly. It's notorious for state, for convergence complexities. Taking it out leads to a massively simplified protocol stack. For network operators, this isn't just academic. It means, faster rollouts, less control plane churn, a network that's just inherently more stable and easier to scale.
Okay, so a simpler foundation. But you mentioned intelligence at the source. This sounds like where network programming comes in.
Precisely. If a segment is one instruction, then network programming is about creating an ordered list of these segments. That's your segment list.
Like a recipe for the packets journey.
Exactly like a recipe. The source device creates this list, sticks it on the packet, and basically tells the network exactly where to go and what functions to perform along that path. This is how you achieve really sophisticated source-based traffic engineering.
Okay, now the part that often confuses people, the IPv6 header trick. How does SRv6 cram all these instructions into the standard IPv6 destination address? No big label stack like MPLS.
Right. Think of the IPv6 not just as a destination, but as a structured space that can hold instructions. The SID, the segment ID, isn't monolithic. It's broken down. You've got components like the locator block and locator node that tells you where in the network this segment lives.
The where. Got it.
Then you have the function part and sometimes arguments. That tells the node what to do when the packet arrives there.
Oh, what? Okay.
And this structure is key. We often use something called the USID or micro SID architecture. It's basically a clever compression scheme. It lets you represent multiple functions or locations very efficiently, which is crucial for hardware forwarding speed.
So you can fit multiple steps in. How many typically?
Yeah. Well, the neat thing is you can usually encode up to 6 distinct instructions directly within the 128 bits of the IPv6 destination address itself. If you need more, and honestly more than 6 is pretty rare for most paths, there's an optional IPv6 extension header called the segment routing header, or SRh. But often, the DA is enough.
6 instructions built into the address. That opens up a lot of possibilities without extra headers most of the time. So let's connect this back to the enterprise user. How does this flexibility translate into real-world services?
Immensely. Because a segment can be any function, the service creation possibilities are huge. You have your topological instructions, things like steering traffic for fast reroute, avoiding microloops during convergence, basic traffic engineering, that's table stakes.
Right, the network plumbing.
Then you have service instructions. Think L2 or L3 VPNs directly signaled via SRv6 SIDs, or network function virtualization, steering traffic through firewalls, load balancers, etc.
Okay, like service chaining, but potentially simpler.
Potentially much simpler, yes. But the really disruptive part, those user-defined instructions we mentioned earlier.
Yeah, tell me more about that. What does that actually mean in practice?
It means the network fabric itself becomes programmable and extensible in ways it never was before. A user-defined instruction could literally trigger any HW custom behavior. Imagine running custom P4 code on a programmable ASIC like Cisco's Silicon One, triggered by an SRv6 SID.
P4 integration. Okay, that's powerful.
Or it could be any SW custom behavior, maybe steering traffic directly to a specific microservice running in a container orchestrated by Kubernetes using an SRv6 SID to identify that service instance.
Wow. So the network becomes aware of and can directly interact with applications or custom hardware functions.
Exactly. It breaks down the traditional silos. Your network isn't just passive pipes anymore. It's an active part of the service logic. Think about an end-to-end policy. You could build a segment list that combines, say, a path guaranteed for low latency.
Using a topological SID.
Right. Then tunnels it into a specific VPN using a service SID, and then maybe chains it through a virtual firewall and then a custom analytics function using NFV and user-defined SIDs, all in one sequence, programmed from the source. That level of granular control was incredibly complex, if not impossible before.
That's a paradigm shift. But with great power comes the need for great reliability. Production networks demand resilience. How does SRv6 handle failures?
That brings us to TI-LFA. Topology-independent, loop-free alternate, it's a critical piece.
TI-LFA, what makes it special?
It provides full coverage with sub-50 millisecond link and node protection. That sub-50 meters is the magic number, faster than applications typically notice.
So seamless failover.
Essentially, yes. And the key is predictability. TI-LFA calculates the backup path based on where the traffic will go after the network reconverges around the failure. It then uses SRSIDs to pre-program and enforce that optimal post-convergence path immediately upon failure detection. No transient loops, no suboptimal routing during failover.
Okay, so reliable protection. What about proactively defining path characteristics? You mentioned network slicing earlier.
Right. That's where flexible algorithms or Flex Algo come into play. This is incredibly powerful for slicing.
Flex Algo. So customizing the routing algorithm itself.
Sort of. It lets you customize how the IGP, like ISIS or OSTF, calculates the shortest path. You define different algorithms, each optimizing for a different metric or constraint.
Okay, give me an example.
Sure. Let's say Algo 0 is your standard IGP calculation shortest path based on minimizing link cost. That's your default, maybe low-cost slice. But then you define, say, Algo 128 to calculate the shortest path based purely on minimizing link latency, ignoring the cost metric entirely. That becomes your low delay slice.
Ah, I see. So traffic marked for Algo 0 takes the cheapest path. Traffic for Algo 128 takes the fastest path, even if it's different.
Exactly. And these paths are computed and guaranteed end-to-end for that specific algorithm or slice, even across multiple domains. You can enforce that low latency path from end to end, regardless of IGP areas or domains. It's true resource partitioning based on intent.
This sounds like it requires a lot of coordination, especially across domains or for complex constraints. How does automation fit in? You said SR is programmatic and automation ready.
It is, inherently. Because the state is at the edge and the instructions are in the packet, It lends itself very well to automation. You get things like intent-based automated steering.
But calculating these complex paths, like a multi-domain low-latency path that also needs to be diverse from another path, that sounds hard for individual routers.
It is, especially for things like path diversity or guaranteeing constraints across multiple IGP areas or domains. Individual routers just don't have that complete end-to-end view.
So you need something central.
Precisely. This is where centralized path compute becomes essential. You use a path computation element, a PCE. The PCE gathers the full network topology, often using protocols like BGP-LS. It has the global view. It can then perform those really complex calculations, finding that latency-optimized, multi-domain, diverse path that satisfies all constraints.
And how does the PCE tell the router which path to use?
It uses a protocol called PCE, Path Computation Element Communication Protocol, to send the calculated segment list back down to the head-end router at the source. That router then just slaps that optimized segment list onto the packets. It combines centralized intelligence with distributed enforcement. Scalable and simple to operate.
Okay, that ties it together. Simplicity in the core, intelligence at the edge, and centralized computation for the really complex stuff.
That's a good way to put it. So if we synthesize all this, SRv6 isn't just another way to forward IPv6. It's fundamentally an IPv6 programming layer. It drastically simplifies the underlying control plane, getting rid of LDP, RSVP-TE, while adding this incredibly granular control and intelligence right into the data plane, into the packet header itself.
So for everyone listening, what are the key things to remember from this deep dive? I would say maybe 3 main takeaways. First, that massive protocol stack simplification. Removing legacy protocols means less state, less complexity, more stability. That's huge operationally. Second, the power of network programming via the segment list. You, at the source, define the exact path and functions, making the network truly tailored to your application needs.
Yeah, programmability.
And third, the ability to hit specific, guaranteed performance targets. Whether it's that sub-50 millisecond protection with TI-LFA or optimizing slices for low latency versus low cost using Flex Algo, you get deterministic behavior.
Well said. And building on that programmability, especially the user-defined instructions, since SRv6 lets you embed custom logic directly into the network fabric, maybe P4 code, maybe Kubernetes integration, here's a final thought to mull over. If you could inject one piece of unique business logic directly into your enterprise network today using an SRv6 user-defined function, what specific capability would you choose to embed, and what competitive advantage would that give your organization? Something to think about.